Nanobots or nanoscale robots are microscopic devices that operate at the nanometer scale, 1 to 100 nanometers. They represent a burgeoning area of technology that combines principles from various fields such as robotics, medicine, material science, and nanotechnology. The potential applications of nanobots, particularly in medicine, are vast and transformative. Here's a detailed overview of their construction, applications in medicine, and other potential uses. Construction of nanobots. 1. Size and scale. Nanobots are typically designed to operate at a scale of 1/100 nanometers, which is about 100,000 times smaller than the width of a human hair. Their small size allows them to interact with biological molecules in cells effectively. Materials. Nanobots are often made from various materials including biocompatible polymers, such as polyethylene glycol, PEG, to avoid immune responses. Metals, such as gold and silver nanoparticles, which can be functionalized for specific tasks. Silica, for structural integrity and capability to carry drugs. These materials are chosen based on their properties like stability, biocompatibility, and the ability to interact with specific biological targets. Design and functionality. Control mechanisms. Nanobots can be designed to be controlled via external stimuli, like magnetic fields, light, or ultrasound, or programmed to react to specific biological signals, like enzymes or pH changes. Self-assembly. Techniques may involve self-assembling structures that react to environmental conditions, wherein smaller units come together to form complex structures. Mobility. Various propulsion mechanisms can be integrated, including flagella-like structures that spin or cilia that beat, allowing movement through bodily fluids. 4. Functional components. Sensing units. Detecting environmental changes or specific biomolecules. Actuators. Performing tasks like drug delivery or targeted therapies. Control systems. Govern the nanobot's movements and functions based on feedback from its environment. Applications in medicine. 1. Targeted drug delivery. Nanobots can deliver drugs directly to cancer cells or infected tissues, minimizing side effects and maximizing efficacy. They can release their payload in response to certain triggers, such as pH levels or specific proteins expressed in tumor cells. Diagnostic techniques. Nanobots can be designed to identify and report the presence of specific biomarkers associated with diseases, aiding in early diagnosis. They can function as biosensors and transmit information to healthcare providers. Cell repair. These devices have the potential to repair damaged cells or tissues at the cellular level. They can be programmed to recognize and fix cellular anomalies, potentially reversing damage caused by diseases like Alzheimer's or heart disease. 4. Gene therapy. Nanobots could be used to deliver genes or CRISPR components directly to target cells, facilitating genetic modifications safely and effectively. Imaging. Using imaging agents, nanobots can enhance the visibility of cells during imaging techniques like MRI or PET scans, helping healthcare professionals to obtain clearer images of affected areas. 6. Antimicrobial action. Nanobots can be programmed to release antimicrobial agents in response to infection, providing a targeted approach to treating bacterial or viral pathogens. Other uses for nanobots. 1. Environmental remediation. Nanobots could be used to detect and clean up pollutants like heavy metals or oil spills, breaking down toxic substances at a molecular level. 2. Nanofabrication. In manufacturing, nanobots could assist in the creation of nanostructures for advanced materials, electronics, or nanocomposites. 3. Agricultural applications. Nanobots could be utilized for precision agriculture by delivering fertilizers or pesticides specifically to areas that need them, reducing waste and exposure. 4. Consumer products. Emerging uses in consumer products include self-cleaning surfaces, enhanced drug formulations, and smart delivery systems that can release ingredients as needed. 5. Energy storage. Nanobots might contribute to the development of more efficient batteries and fuel cells by optimizing the arrangement and interaction of nanoscale components within the devices. Challenges and future prospects. While the potential of nanobots is enormous, challenges remain: safety and toxicity. ensuring that nanobots do not cause adverse reactions in the human body. Regulatory framework, establishing guidelines for the approval and monitoring of nanobot technology. Technical limitations. Improving the control, navigation, and power supply for nanobots in complex biological environments. In conclusion, nanobots represent a frontier in technology,